Hi guys, this is a video for those of you who might struggle in the multiple choice. I did it because maybe it can help some of the amazing people that I met this semester. Adrian, Priscilla, Denzel, Franco, Prince, and I'm probably leaving someone else. But anyways, what I'll do is that I'll go over the way I do the multiple choice and how I think about it so that you guys have an idea of how to approach those type of questions. So if you had to take just one advice from this video, it is always check your assumptions. If you have something wrong or if you're confused about something, it's because one of your assumptions is wrong. And the general way to approach these problems is by making assumptions first. For instance, this is going to be the first problem. Two identical objects A and B fall from rest from different heights to the ground and feel no appreciable resistance. If object B takes twice, you know what? If you want to read it, just pause the video. So from here we can assume that the initial heights are different. So that's going to be first is not the same as HB, but the objects are identical. So MA equals MB. Not that it matters anyways. Now, they fall from rest. That means that this is a free fall situation. Therefore, force of gravity is the only force acting on the objects. No air resistance, so it's just force of gravity. And from that follows that the acceleration of the objects is only g. Now, they tell us that the time that it takes, and so they tell us that object B takes twice as long as object A to reach the ground. So the time that it takes object B is 2 times the times that it takes object A. And what they're asking is for the ratio of the heights. Now with these assumptions, we can create an equation for the height. Oh, and by the way, I forgot to add something. They both reach the ground, so final height, I'm going to call it H0, is the same. And so with this, we can create an equation that gives us time as height as a function of time, because we have all the necessary variables. We have the acceleration. We know that it goes from rest, so initial velocity for both equals 0. So the position equation is just this formula, x equals xo plus VO time plus A times square over 2. And then if we put it on this notation, we can just have that the final height, which is going to be HO, and that's the ground, equals the initial height for A is HA plus VOT is 0, it cancels out for both, plus the acceleration times A, right? The time it takes A squared 2. And for B, it's going to be H0 equals HB plus, now we need to write this times B as a function of time A, right? So we know that times B is 2 times A, so we can write instead of time b, 2 times a. And we have to square this because the variable goes squared. And now we have all we need to solve because we can solve this for HA and for HB, and we get that HA equals HO minus A times A squared over 2, and HB equals HO minus A times 2 times A squared. Now for simplicity, you can say that the ground is height equals 0. So this is 0, this is 0. And now we just need to make the ratio, right? So they're asking about h of A over h of B. So h of A over h of B is dividing those two equations. We get negative A times A squared over 2 over negative A 2 TA squared over 2. Now all these variables cancel out. It's 2, this negative, and we get that TA squared over, now 2TA squared is the same as 4TA squared, and the TA squared cancels out, so we have that the ratio is 1/4. Okay, now let's go to another question. Jan and Len, well, you can read this. You can just pause the video. So assumptions that we can make. Well, they throw the same from the same point, the rock from the same point. So initial height, I'm gonna call this HO, is the same. They have the same final height, so H is the same. Jan throws a rock straight downward, and Len throws his rock downward and outward. So they both have initial velocities, which I'm gonna call VOJ for Jan and VOL for Len. And they tell us that Len throw his rock with twice the speed of Jan's rock. So this is 2 VOJ. Len throw his rock downward. So we can kind of make a graph here. Right, this is going to be the building. And so Jan's wall goes downward and Len's ball goes this way, making a 30-degree angle with the horizontal. Okay. Now that we know this, and since this is also free fall, we can assume that they both have acceleration equals g, and air resistance is negligible, so it doesn't matter. And the question is, which rock hits the ground first? Well, for that we need to know the initial velocity in the y-axis, because all that matters here is the y-axis, since we're just asking about how much it took to travel this vertical distance, right? And since they're under the same acceleration, the only difference in their motion equations is going to be the initial velocity. So whichever has a greater vertical initial velocity is going to reach the ground first. In this case, we have that VOJ is entirely the y component. But what about VOL? What is the y component of length stroke? Well, we can do some trigonometry here. This is 30 degrees. And so the y component of this velocity is this, which is going to be the sine of 30, v sine of 30, the magnitude of the velocity sine of 30. And we know that v is VOL, which is 2VOJ, so 2VOJ sine of 30. Now, sine of 30 is 1/2, and so 1/2 times 2 just cancels out. So the vertical component of length stroke is exactly VOJ. So they have the same vertical component. That means they both hit the ground at the same time. This one's fun, okay? This one is all about frame of references. So if you're standing in a moving bus facing forward and you suddenly fall forward, what changed? Something change about you, or did something change about the bus? Well, it is a given that the bus comes to a stop. So there's something changing about the bus. Is there something changing about you? Not really. At least they don't tell you. And so since the bus comes to an immediate stop, that means that the bus is accelerating backwards. In the meantime, you are just moving at constant velocity. So acceleration implies a force. Velocity does not imply a force. The one that is accelerating is the bus. So the one that is being sustained to a force is the bus. Therefore, no forces were acting on you to cause you to fall. So we have to pay attention to which objects are being analyzed in the moment. Oh, this one's nice. Okay, so work is a scalar quantity that is defined as force times displacement. So as long as both force and displacement are in the same direction, the work will be positive. So if both of them are negative, so negative times negative is also positive work. So let's just analyze that. Picking up the boxes of tomatoes from the stockroom floor. Well, the force that the guy is doing is up. And where are the boxes moving? Well, the boxes are moving up. Same direction, that means that this is positive work. Accelerating to a comfortable speed. So the guy is applying a force to accelerate, and the object is moving towards the direction where it is acceleration. Same direction. Perfect. Carrying the boxes to the tomato display at constant speed. So when an object is moving at constant speed, you do not have to apply a force. The force, therefore, he's not doing work on the object. Decelerating to a stop. Okay. So that means that the object is still moving this way, but now he's applying a force to create an acceleration in the opposite direction. So opposite directions, work is negative. And now lowering the boxes slowly to the floor. So since it's lowering the boxes slowly, that means that he's somewhat canceling the force of gravity by still holding the object up. So still applying a force up, but the object is going down. So opposite directions, this is also negative. So the answer is 1 and 2. Oh, this one's nice. A cup of water containing an ice cube at 0 Celsius is filled to the brim. Right? So I have a cup of water filled to the brim. And I still have an ice cube here. So what we know about this situation is that since this is floating, the mass of displaced water equals the mass of the ice cube. Why? Because, well, the forces acting on this ice cube are buoyant force and force of gravity, right? They have to be the same so that the object is not moving up or down. So we have that buoyant force equals force of gravity. Now, force of gravity is just going to be the mass of the ice cube times gravity, and buoyant force is just going to be the mass of the water displaced times gravity. Or in other words, this is volume displaced times the density of water. And this, the mass of any object, following from the definition of density, is volume of the ice cube times density of the ice cube. Okay, so this is true at all moments. It doesn't matter how much mass the ice cube has or how much mass it's displacing. What is also true? Well, the amount of mass is not going to change in this situation. Okay, so knowing that, let's look for a relationship between volume, right? So volume of displaced water, which is what we care about anyways, equals mass of the ice cube times gravity. Oh, sorry, no, gravity cancels out, right? And so the volume of displaced water equals the mass of the ice cube divided by the density of water. Now, this equation is true no matter what is the mass of the ice cube. But as it melts, the mass becomes smaller, but the ice cube will still be floating. So this has to be true. And so once the volume of the ice cube is completely melted, all of that mass becomes, so the mass of the ice cube is now liquid water. So the volume of the ice cube when it melts as liquid water is the mass of the ice cube divided by the density of liquid water, which is what the ice cube is now. And so these two expressions equal each other. So the volume of the ice cube as it melts is the same as the volume of displaced water at any moment when the ice cube is floating. So it never overflows, it never goes down, it remains at the same level. Okay, let's do this one. And that's going to be the last. So planet C34 has a mass equal to 1/3. So it's planet C. Mass of planet C equals 1/3 mass of Earth. Radius of planet C equals 1/3 radius of Earth. And actual spin, I'll just keep it in mind, but actual spin, I'm going to call it AS, equals 1/2 actual spin of Earth. We'll see if we need this, because this could be useful to get centrifugal acceleration. So with G representing as usual the acceleration due to gravity on the surface of Earth, the acceleration due to gravity on the surface of C34 is. So where does G come from? Well, we know that the force of gravity equals G m1 m2 over r squared. And we know too that this terms over here is what we call the acceleration of gravity. So now we only have to compare this value at Earth with the value at planet Z. So let's write the expression for Earth. So G, which is this expression, G at Earth equals G mass of Earth over radius of Earth squared, and G at planet Z equals G mass of Z over radius of Z squared. Okay, so now let's just get a ratio so that we know an expression for G of Z in terms of G of E, right? So we can do G of Z over G of E. I always put the one that I want to get on top. You'll see why. Equals, and now it's just plugging in the equations, right? G mass, so the one in the numerator is the mass of Z, and the mass of Z is 1/3 the mass of the Earth. So I'm just going to put 1/3 mass of the Earth. Also, I forgot to put the radius of Z is 1/3 the radius of the Earth. But keep in mind that this is all squared. And now in the denominator is the expression for Earth. So this is G m at Earth and radius of Earth squared. Okay, so we can develop this and square all this. So this is going to be E 1/3 me over this squared is 1/9 re squared over just G me over radius e squared. Okay, and now we can just cancel out basically everything, right? So this with this, this with this, this with this, and we multiply times gravity on Earth so that we move this term to the numerator. So let's do that. Remember that we have 1/3 here and 1/9 here. So G of Z equals 1/3 over 1/9, and all of that multiplies GE. And so 1/3 over 1/9 equals 3GE. And that's going to be your answer. What should be here? Okay. It's this one. Perfect. And it looks kind of weird because, yes, it is 1/3 the mass and 1/3 the radius. But keep in mind that this is the force at the surface of the planet. And since the radius is 3 times smaller and the radius weights more into gravity because it's squared, then gravity is 3 times bigger. Anyways, I'll leave it here because I'm tired, but I hope you guys learned something.